de la thèse de Hugo Vallée qui a été effectuée en collaboration avec NXP Toulouse et l'Université de Bordeaux. Donc, M. Vallée, le jury est réuni en visio. Donc, vous avez vos deux rapporteurs, le professeur Bourdel de Grenoble INP, le professeur Zito de Aarhus Université. Vous avez les membres de NXP qui ont suivi de près ou de loin vos travaux, donc M. Ours, M. Landez et M. Montoriol, puis votre directeur de thèse, donc Thierry Taris, et moi-même, Jean-Baptiste Begueret, professeur à l'Université. Donc nous allons vous laisser 45 minutes pour la présentation de vos travaux de thèse. Et écoutez, je vous laisse la parole.
Thanks, Mr. Chairman. Thanks to all to attend to this presentation of the design of receiver in microwave domain for embedded automotive radar in advanced CMOS. This work has been done in partnership between IMS Lab in Bordeaux and NXP Semiconductors in Toulouse. This presentation is divided in 4 sections. First, some highlight of the automotive radar context, defining the top specification of the receiver we will design then. And then 3 research axes, one on active mixer exploiting noise cancelling principle, then on low noise amplifier exploiting also this noise cancelling principle, and then designing a complete passive baseband band converter. So first, what is the industrial context of this thesis? In automotive industries, we have 2 major trends. First, have safer vehicles, more autonomous vehicles. To achieve this automation, a large panel of sensors is required. You see some of them here. So first, we can see camera, which are used for recognition and identification of vehicles, LiDAR, which is a good solution for environment mapping, and secure communication to connect with the surrounding objects. These various sensors are complementary, and in this context, automotive radar presents few advantages. First, a good reliability to outdoor conditions, weather, night, a simultaneous measurement of distance and velocity, and also a flexible use with short-range application to monitor surround car, vicinity of the car, and long-range application for adaptive cruise control, for instance. Now we can ask how we perform this measurement of distance and velocity. For distance measurements, so for this type of radar, we used FMCW, so frequency modulated continuous wave modulation with fast chirp. The distance measurement is performed through the difference between the transmitted and received signal. So the frequency varies, as we see on these figures. So on the bottom right, figures, and we measure the difference between each transmitted and received signal to define the distance of the targets. In fast chirp modulation, we use a frame of several chirp, and we measure the velocity thanks to the Doppler effect, and this Doppler effect information is embedded in the phase of the signal. So we perform a second FFT on N chirp to measure this velocity through the Doppler frequency. What are the advantages of the FMCW modulation? We have first a simple generation for the RF part and a simple signal processing and digital processing at the output. That's why this modulation is most used for automotive radars. Now, if we have a more look on the radar modules that can be used in car. So, second. So we see here two examples of radar modules with few elements which are always present. First, an antenna array can be seen here and on the bottom also, which transmit and receive the radio frequency signal and define, thanks to antenna gains and aperture, the use case from short range to long range application. We have then RF transceiver, which is for this. That is the core of our design, which transmit and receive the millimeter wave signal. Then microcontroller units are used for the digital processing. And finally, power management circuit is used to provide the power supply to the different subsystems of the radar modules. First, for the transceiver design, we have to select relevant topologies. That's why we define a form factor which is linked to power consumption and silicon era. These parameters are quite critical for the price of our industrial products. Power consumptions can be linked to thermal dissipation management, and silicon era can be linked to the unitary cost of the radar IC, as we see here. And we can select various topologies from 3 to 5 topologies, BiCMOS or RF CMOS. Historically, we used the BiCMOS technology because this type of technology provides high RF performances linked to transition frequency, power gain, for instance, for moderate integration, which is sufficient for high-level products. Now, advanced RF CMOS, such as 28 nanometers, present competitive RF performances, as we see on this graph at the bottom, and a high level of integration, so a very low cost. That's why we select in this thesis to 28 nanometer technologies to design our circuits. So we see with this first slide one of the key figures of merit of a radar IC. Now, if we have more look on the architecture of a radar IC, what we see? We see some baseband or digital or analog blocks here. And 3 key elements, so the PLL, so the phase locked loop, which synthesize the LO signal with one critical figure of merit, which is the phase noise, useful for the object separation. The signal is then transmitted to a transmitter, which amplifies the RF signal, and a key figure of merit can be defined by the output RF power linked to the range of our circuits. Then we have the receiver, which then converts the millimeter wave signal and process it up to the ADC, where it's converted for digital. And the key figure of merit for this block is more the noise figure, which can be also linked to the range. Now, how we can define the specification of this RF demodulator here. First, for noise, we have to consider 3 mechanisms to define this noise specification. First, we can have a high-level view, a top view, with the emission, reflection, and reception of radar signal, which you can see at the left of these figures, and some top-level characteristics for the radar IC, which links the maximum range here on the top to the noise figure of the demodulator. Now, if we consider the distribution of noise over the demodulator chain with a PCB to IC interface, with the receiver, the millimeter wave front end, and then one or several baseband stage, we see that for low noise figure for the millimeter wave front end, the noise of the other block are predominant. And for high noise, this is this block which impacts the overall noise figure. Then we have a third mechanism, degradation mechanism, linked to a poor isolation or a moderate isolation between the transmission and reception, linked to a leakage of RF power at the input and the down conversion of the encoded phase noise of this leakage power with the LO power. And then we increase, in fact, the noise floor at the output, leading to a degradation of the overall noise figure. That's why we consider in this work for long-range application that the noise specification of 15 dB is sufficient. Now, if we have look more on linearity, which is also very important for radar, we have three scenarios for linearity. First, a single target scenario. In this scenario, a target reflects a signal with a high power because the target is very close to the radar antenna. We can have, if the unit is too low, corruption of the information with several tones. That's why we define an in-band compression point. Then we have a two-target scenario with the intermodulation of the two signals in the receiver, which creates some tones, and these tones, if they are too high, can be identified as a false target. So that's a nightmare for the digital processing because we have several false targets in all the spectrum. That's why we define the input intermodulation product here, specification. And finally, we see that the antenna array are placed behind the bumper of the car. So we have a high power reflection on this bumper, which comes at the antenna input and the receiver input. This high power jammer can pollute the whole frequency bandwidth, not with the down conversion of the signal, because as we see on the top, this bumper is very close to the LO frequency, so we don't see it in the IF band, in the down converted band, but it can create intermodulation products. It creates intermodulation product, but if these intermodulation products are too high, we'll pollute our IF bandwidth with false targets. That's why we define this TOF specification of -7 dBm of input compression points. Finally, we see in this first part that 80 GHz radar is key for vehicle automation because it allows simultaneous distance and velocity measurements, a good robustness to outdoor conditions. But this use case leads to define specific requirements. First, in this table, we see at the top that we have 76 to 81 gigahertz of RF bandwidth, and the down-converted signal go from 1 megahertz to 40 megahertz. Then we define some noise specification with the several degradation mechanisms highlighted. So for short-range radar, we have a relaxed specification of 17 dB, and for the long-range specification, we have a tau specification of 15. And then, due to this bumper reflection, we have a high linearity specification of -5 dBm for input compression points. We then have some objectives which are not deadline, I would say, of conversion gain and power management. One thing which I want to highlight is the automotive condition, how we produce industrial products. We are not in typical condition of temperature and process. We have to consider in our design process variation with the three defined corners from slow, typical, and fast corners. Important temperature range from -40 to 150 degrees, and a voltage supply variation of plus or minus 5 percent. So first, in this thesis, we work on active mixer exploiting noise cancelling. In this part, we'll detail first how to build a noise cancellation based on common gate approach. Then the first implementation in RF domain for RF demonstrator, and then a millimeter wave noise cancelling mixer exploiting these two approaches of active and noise cancelling. Usually, we can define two main approaches for matched topologies. First, resonant matching approach, and then non-resonant matching approach. The resonant matching approach is can be shown with these common source topologies, which present high RF performances and a matching which is linked to some inductive elements. It can lead to narrowband matching, depending on the quality of this passive, obviously, and be sensitive to PVT variation. In non-resonant matching, for instance, with these common gain topologies, we can achieve wideband matching, controlling by the biasing of the transistor, but moderate performances, especially in noise. The noise-cancelling approach proposed to combine these two types of topologies using a main stage, which is used for matching. It can be, for instance, wideband with a common gate topologies. That's what we select for this work, so it presents a wideband impedance matching, but a poor noise performances. That's why the auxiliary stage is used to sense the noise of the main stage and cancel it at the output. So how we can implement these topologies. Here we see a common gate-based noise cancelling mixer. First, we have a condition on impedance matching. We see here we have the two paths. So we have here at the top the two switching quad. We have the load and the input transconductance stage at the bottom. Here we have the main path, which is common gate 1. Here we have the auxiliary path, which is common source 1. So for input matching, we can consider that the common source path presents a high input impedance. So we will neglect this path. That's why the input impedance is linked more to the common gate transconductance. So we have a condition between the source resistance and the transconductance of the common gate path. The second condition will be on gain imbalance. As we have an inherent asymmetrical topologies, we have to ensure that the signal which go on the common gate path and the common source path presents the same gain. So we have a link between transconductance of each path and the load of each path. These two conditions allows a noise cancellation of the common gate noise current, which is here. This noise current creates two antiphase voltage, one at the output, one at the input, and this last one is then amplified and then converted by the common source path, and we have at the output two in-phase equivalent voltage, and then we have the cancellation when we apply a differential measurement at the output. These topologies have been first implemented for RF demonstrator in C28, typically for multi-standard RF application from 1 to 10 gigahertz, requiring multi-standard wideband transceiver. We have several implementations for both noise reduction and better current efficiency. So between the two paths, fulfilling the condition 2 we highlighted before, we have a topological factor used to reduce the noise contribution of the common source path. We also used an inverter-based approach for the common source path to have a better current efficiency, and we implement two design techniques using the design moderate inversion to increase the efficiency of the overall circuit, and also some flexibility on the first condition of common gate of noise cancelling approach, and the flexibility on impedance matching to have some power saving. That's why we define some measurement in two modes of operation. We see here also nominal and power saving mode. For both, we have a wideband input matching on the top figures and a low noise figure. The mode of operation impacts more the noise bandwidth, especially for power saving mode. For conversion gain, we have moderate to high conversion gain, and the bandwidth is not impacted by this mode of operation as it is for the linearity, which is quite high for this low current, because we have a power consumption which is below 4 milliwatts and even 2 milliwatts for the power saving mode. So we see here the interest of the noise cancelling approach to achieve wideband and low noise and low power consumption circuits. Why we decide to implement it in millimeter wave and especially for radar application. First, the noise cancelling approach presents a wide bandwidth and a good robustness to PVT variation, which is critical for application. The active matching and the active allow some post manufacturing adjusting, and the active balloon is used for better conversion gain. Why do we use active mixer? First, because the good trade-off between noise performances and linearity, and the high conversion gain, which reduce the analog baseband noise. And finally, moderate power consumption. The main issue of active mixer is more on flicker noise. In active mixer, we have important flicker noise which generates at the gate of the transistor. Sorry. At the gate of the transistor, this flicker noise can be linked to both parameters. First, the technology length, which is critical because we use deep CMOS technology, so it's very high, and at low IF, and we see that our IF bandwidth came from 1 MHz to 40 MHz. This noise mechanism is generated by two mechanisms of generation. First, the direct mechanism, which is linked to the switching events. So we have noise generation during the switching event, depending on the overall current. So to reduce it, we use the current bleeding to reduce the current in the switch, and it leads to a reduction of the noise. The indirect mechanism is linked to the parasitic load capacitance at the tail of the switches. That's why we use an inductor to cancel these parasitics and achieve a 3 dB reduction of the overall noise figure at 1 MHz and a division by 2 of the flicker noise corner, which is significant. Then we can also question the selection of noise cancelling approach to millimeter wave, for millimeter wave design. First, we see some interest because for mixer we use low impedance node, so at the reactive part of the input impedance is fully linked to the transconductance of the common gate transistor. And obviously, as we have some parasitics, especially capacitive parasitics, we cancel it thanks to this input inductance. That's why we can achieve wideband real input impedance. For conversion gain, we can have some imbalance due to this unbalanced asymmetrical topologies. But we see no common mode in measurements. And obviously, parasitics can also impact the noise cancellation. The diagonal noise of the common gate transistor is not fully cancelled, as we see. In post-layout simulation, we see that a third of the common source noise remains from the common gate transistor. So we have not a fully noise cancellation of the common gate noise. This circuit has been implemented in C28. Sorry. Ça a compté, je crois. Sorry, it's my circuit. Sorry, my PowerPoint failed to open. Need a few seconds to reopen it, sorry. So here we are. So we implement this noise cancelling mixer in 28 nanometer CMOS technology, and we perform post-layout simulation considering the process and temperature variation and some measurement in typical case. So here you see at the left graph is the post-layout simulation considering the temperature variation linked to the color of the line and the process variation linked to the dashed of the line. Line dashed are slow and fast process, and continued line is the typical one. On the right part, you have the measurement simulation with some post-layout simulation in typical. So we see that we have a wideband input matching robust to PVT variation. Due to some issue on access parasitics extraction, we underestimate the access parasitics, leading to marginal but still wideband input matching. Now we can have a look more on the conversion gain, linearity. So here we see the conversion gain. So we have at the left the PVT simulation. So we have moderate gain around 14 dB, but wideband and robust PVT variation. In post-layout simulation, we are close to, in measurement, sorry, we are close to the post-layout simulation and around 14 dB of gain. Now, if we look on linearity, we fulfill the specification in post-layout simulation and in measurement of -5 dBm of input compression points. Now, if we have a look more on noise performances, we see that the noise figure in typical is moderate or even low, around 13 dB, which is quite good. But we have an important impact of PVT variation, especially at hot and slow corner, which we see at the top. We have a high noise figure around 19 dB, which is very important and too high for our application. Now, if we have a look on flicker noise, we see that the noise figure presents also important variation, especially at 1 MHz, but reduced thanks to these noise reduction techniques. In conclusion, we see at the right that we can link the range to the performance of our mixer. So we do the bottom-up studies to place these performances in a modeling of our demodulator to see what range we can expect. We see that in the worst case, the maximal range is close to 80 meters, so this type of architecture can be suitable only for short range radar. Nevertheless, noise cancelling architecture achieve high RF performances with an interesting trade-off between RF performances, power consumption, and a good robustness to PVT variation. Nevertheless, active down converter cannot be used due to this issue of flicker noise. Now, if we have a look more on noise cancelling amplifier, low noise amplifier, sorry, we will detail first the LNA specification in a conventional architecture, and then two types of LNA. So here we have an example of conventional architecture of a down converter. We have first the millimeter wave front end, here in blue, with LNA, which is used to increase signal level with minimal impact on noise and linearity. The mixer, which is used to down convert the input RF signal to baseband and combine high-pass filter and VGA to reject the bumper, as we see on the left of these figures, and increase the signal level. So we have to find a trade-off between two phenomena for the LNA specification. First, we may increase the LNA gain to reduce the overall noise figure, but if we increase LNA gain, we limit our overall input compression point linearity due to the mixer linearity. That's why we found a trade-off between this specification, and we prefer, I would say, a one-stage LNA. Our first idea is to use a millimeter wave noise cancelling LNA. In these topologies, the noise cancellation is performed in millimeter wave domain. So we will have an impact of this type of selection, I would say, of mode of operation. This has been implemented in C28, and we have only post-layout simulation for process and temperature. We see that we have a low power consumption and a low voltage supply, and we achieve a high conversion gain, but we have poor performances in noise, especially at hot, where we go up to 9 dB of noise figure, which is too high. The other issue is more on output balance. We see that as we perform the noise cancellation and we have an asymmetrical topologies, we may have some imbalance phase and gain between paths, and it can create issue on this balance architecture over the demodulator chain. That's why we developed these complementary capacitor cross-coupled topologies, which used for the amplifier core this circuit. We applied the input signal at the top and at the bottom, and we use an inverter-based cell, GM cell, which double the transconductance without impacting the current, so the power consumption. We use this complementary approach to also double the GM of each transistor without impacting the DC current. So we expect a high gain with a very low power consumption. Besides, we have partial noise cancellation of the noise of each transistor, and to perform this, to apply, I would say, the input voltage at the top and at the bottom of the GM core, we use a signal splitter, which is also used for DC decoupling, and we implement it through a transformer here. So a transformer with one primary and two secondaries. And the ratio of this transformer can impact the mode of operation, and we see now how to select this transformer ratio and mode of operation. It can be linked to two modes of operation. The first one is the low power mode. We have important power saving, but lower gain. And for the high gain mode, we increase the DC consumption and the gain. So we can select one or the other mode of operation, depending on the specification of our product. Interestingly, the noise figure is not impacted by this mode selection. So for our case of radar, we select a transformer ratio of 1 because it achieves a moderate gain linked to the limited specification on mixer linearity and a moderate power consumption. Here we have an example of implementation in C28 with this transformer, so one inductive element, a core, which is here and also shown at the bottom. This has been a DC current source used to bias the circuits. And this has been simulated, manufactured, but not yet measured. And it presents in simulation low power consumption, below 4 milliwatts. We see in post-layout simulation, first on input matching and noise, that we are wideband and quite robust to positive variation, depending on the load impedance. And also for noise figure, we present a low noise figure around 7 dB at 0.5 dB in worst case. So it's better than the topology we had before. Regarding more now gain and linearity, we achieve high gain for one stage linear, close to 10 dB, with a moderate variation over PVT here. And now if we look more on linearity, we are higher than the specification of -5 dBm. Sorry. Yes. So in conclusion, we see that these topologies, thanks to the complementary approach and the cross-coupling, achieve low power and a lot of power saving. And thanks to the common gate-based topologies, we have robust and wideband input matching and good robustness to PVT variation. We see also that we have a very compact topologies, and which achieve high performances, especially regarding linearity, good conversion gain, and a competitive noise figure regarding the state of the art and the application, because in typical we have 4 dB of noise figure. That's why this topology is a good candidate for down converter implementation. Now, we try to implement these topologies in passive beta down converter. So we developed 2 of them, voltage mode and current mode. Here we have the proposed voltage mode front end implemented in a complete demodulator. We have first one stage C4 LNA used for this good trade-off between RF performances and power consumption. Then we have the passive mixer followed by the variable gain amplifier combined with a high-pass filter. Here, this block presents a high input impedance, so we have a high baseband impedance. And due to the transparency of the passive mixer, this input impedance is up-converted at the input of the mixer and impacted by the parasitic capacitance. As we have a high input impedance, the parasitic capacitance impacts have a lot of impact on this impedance. As we perform a voltage down conversion between the input and the output of this passive mixer, we may have an important voltage swing at LNA output affecting the receiver linearity. The HPA VGA is designed to improve the noise rejection of the following block using a low noise VGA with high gain and reduce, thanks to the high pass filter, the bumper which is below the IF band. The millimeter wave part of this down converter have been implemented in C28 with a low power consumption of 24 milliwatts, and some post-layout simulation have been proposed considering the process and temperature variation. First, if we look on input matching, we achieve moderate, I would say, input matching, especially regarding the PVT variation. Not all the band is covered, but it's still, can consider it as wideband in typical, but have a moderate robustness to PVT variation. Now, if we have a look on noise figure, present a very low noise figure for real mixer of 15 dB in worst case, with low flicker noise corner. This noise performance is then fully compatible with the specification we define for long-range radars. Now, if you have a look more on conversion gain, we see that we present a high conversion gain, higher than 16 dB, with an important variation due to PVT, which can be compensated by gain calibration in the baseband stage, especially for the VGA. The main issue of this topology is on linearity. We see that the in-band linearity leads to the one target scenario. We are above the spec, so that's quite good. But for the tau specification of -5 dm, we are below the specification. So even if we have high linearity in absolute, we are limited for our application. That's why we should select another topologies. In conclusion, we see here that we implement the proposed down converter in the complete demodulator chain. We see that we can target a long-range application up to 200 meters, because we achieve a low noise figure, but we cannot handle the bumper reflection. That's why we use a current down converter. So we have the similar architecture using a transconductance amplifier before the high HPA VGA. As we see here, we have a low baseband impedance, which is up-converted at the input. So we have a low input impedance affected by the switch resist on resistor. And as the real impedance is low, we do not have a huge impact of parasitics. We use this I2V conversion in the TIA with a minimal impact on the noise performance. The millimeter wave part have been implemented we see that we increase the power consumption compared to the voltage mode due to because we add one stage TIA, and we show only PVT simulation. For noise input matching, we see that we are wideband and more robust to PVT variation, so the overall RF band is addressed. For the noise figure, as we add TIA, so stage, the noise performance is degraded compared to the voltage mode, but we are still compatible with the specification. If we have now look on conversion gain, we achieve a high conversion gain, more wideband and more robust to PVT variation compared to the voltage mode one specific non-comparator. For linearity, we are fulfilling the specification of -5 dBm, even in worst case. So that's non-converter seems to be more suitable for long-range application. We see at the right that we can achieve 200 meters using this non-converter without with a good robustness to PVT and robustness to the bumper reflection jammer at the input. That's why the current mode non-converter using the C4 amplifier we developed before can be used for long-range radar, achieving high performances and low power consumption. Conclusion, we see that passive non-converter have few advantages compared to the active one. First, the no flicker noise. We can use ELENA and mixer co-design to improve the current efficiency, which have been shown by two passive mixers. First, the voltage mode, which achieve a low noise but a limited linearity if we compare to the TOUT specification of automotive radar, and the current mode passive mixer, which provide adequate performances for radar module, especially regarding linearity, even if the noise is a little degraded due to the TIA, but we are still compatible with the specification. In conclusion, first, I want to highlight some points of the automotive radar. First, 80 GHz radar is key for vehicle automation because it allows simultaneous measurement of distance and velocity and a good robustness to PVT to outdoor conditions. Sorry. It leads to the first part is to define some requirements for the receiver, especially regarding linearity due to the bumper. Moderate noise figure is required for long-range and short-range application, and the moderate gain because of the trade-off between the overall noise figure and the overall linearity. We have to consider for industrial products automotive condition regarding process, temperature, and supply variation. In this work, we developed 5 circuits. First, some active mixer, an RF demonstrator applying noise cancellation, a millimeter wave noise cancelling mixer, which demonstrates this topology, at 80 GHz. Then 2 LNA, one has been implemented, so it's a complementary capacitor cross-coupled LNA have been implemented in a circuit not yet measured, and 2 RX front-end implementing passive mixer and LNA, the C4 LNA. If we compare to the specification, the noise cancelling active mixer is not completely fulfilling the specification. Voltage mode non-converter present a lower linearity compared to the specification, and current mode non-converter seems to be more suitable for this application. The overall contribution of this thesis to the state of the art will be to compare various architecture, so active mixer, which achieve good trade-off between RF performances and form factor, and exhibit a high flicker noise, Voltage mode passive mixing, which achieve low noise and moderate gain, but limited linearity if we consider large signal processing. Current mode passive mixing achieve moderate gain, but high linearity, the noise performance is degraded by the TAA, but is still low. And we implement several design techniques. First, noise cancelling technique, which achieve good RF performances over large bandwidth, which have been demonstrated in meter wave. From these topologies, we develop the complementary capacitor cross-coupled arrangements, which achieve high RF performances for reduced power consumption. And finally, we work also on low power technique, especially the design in weak inversion and the use of complementary structures. This work leads to several publications in journal or conferences and one ongoing patent. I want to thank you for your attention, and if you have any question, I will be pleased to answer to this question.
Thank you very much. Thank you, Mr. Vallée. We will now go through the usual question and answer time. And we will begin by the reviewers who have particular look on your manuscript and your work. So we will begin by does Professor Zito is online? Domenico?
Yes, I'm online. I'm online.
Hi, Domenico. So it's your time now to ask questions if you need.
Okay, so thank you very much, everybody. And sorry again for the connection issue at the very beginning. But as I said in the email, so I haven't lost any word. So I would like to thank you for inviting me to this PhD exam. And I would like also to thank Hugo for the presentation and the hard work with a lot of challenges that he went through. I had already a number of questions coming from the review of the manuscript, and I wouldn't go through them. I would like to ask 2 quick questions, and I would like to say that the role of this question is that somehow we have seen many things, we have seen a number of challenges. It's been, my understanding is that it's been a wonderful gym for getting strong on many concepts. I think all these things, all the challenges you faced will make you stronger for the future, and I'm convinced that you will you understand a lot. So let me ask these 2 questions. That the role of this question is to see somehow your ability to review your work yourself, right? Kind of self-review. In your presentation, in slide 30, you mentioned that it's interesting that the noise doesn't, let's say, doesn't vary much in the mode selection versus the mode selection is essentially unchanged. Can I ask you why it's interesting, or in the sense that it was something that you expected, something that you didn't expect? Why is so interesting? I understand that it's good. This is clear. We don't want this to happen because we want performance. Let's say, in principle, equal performance over the bandwidth. But why is it interesting, and it's a surprise?
Yes, it was a surprise because we are not used to consider that changing the transformer ratio or the transistor sizing will impact the noise figure. Because we use, in fact, the input transformer as a voltage state up or the voltage state down, and the transistor GM will change to have a matching operation. So to have a matching operation, this transformer ratio will impact the transconductance sizing of the common gate transistor we see before. We just remind you this the topologies here. So we have an impact of the transformer ratio at the bottom on the sizing of the N or NP transistor. We see it here on these figures here, the blue one, the blue curves. And in fact, for the noise operation, the two phenomena, changing the ratio of the transformer and the unitary transconductance to have match operation, leads to have the same noise figure, but not the same gain. We do not have the same transfer function for noise and gain. Why it can be interesting? It's interesting because, especially if we want to achieve low power mode of operation, because at low power we can have issue of noise because we have small transistor, and with this topology we know that for a low power mode we can achieve a low noise, which are at the best at 1.3 dB of noise figure, or in RF domain, of course, with a very reduced power consumption, because we see that we have a 4 milliwatts, so we can achieve even below 1 milliwatt of power consumption with this low noise figure. That's why I say that I think that it's interesting technically, and for our application, for what application can target, to have this constant noise figure, which do not depend on transformer ratio. Do you want me to?
Please go ahead.
Yes. So that's why it's interesting, because the noise figure do not depend on transformer ratio. So even if we go in very low power consumption, we can achieve low noise figure without any impact on the noise figure. And if we want to have more gain, we can also achieve high linearity, and because we have high power consumption and high gain without impact on noise figure.
Still not clear to me so you mentioned that it was a surprise. Why it should be a surprise if you used an LNA, which is wideband, and a mixer, which is essentially...
I can show you some calculus. Maybe 2 seconds time to open it. So it's open. In fact, in the calculation, so we have two different approach, two different transfer function for noise and gain. So I will open my slide here. Here. So here, for instance, for gain, we see the definition of so here's for input matching. So we have condition of input matching, so we can link, in fact, on this calculation I don't have the pointer, but at the bottom we can link the transconductance of each transistor, so it's a unitary transconductance, to the transformer ratio, because the transformer ratio impacts the output impedance of the transformer. So if we have at the bottom right equation, the output transformer, and can be linked to the GM of each transistor. So we have this first condition to have matched operation. Considering this condition, we can define the transconductance of the LNA, this LNA, which is linked to the transformer ratio and the input resistance, so the source resistance, I would say. Now, if we have looked more on noise, so we see that here we have a linear link between the transformer ratio and the transconductance. If now we have look on the noise here, in fact, the output noise current is we don't have the same transfer function from the resistance noise, which is amplified, and the reduction of the noise of the N plus or of one of the transistors. So we see here the partial noise cancellation, and when we do the calculation, we go to this noise figure with the transistor N or P transistor noise on the resistance noise, And making this calculation leads to considering the matching operation here for the GMRS, which I have here. We have this constant noise figure at the output. So it's quite interesting because we have topologies which are different but not so far from these topologies, and we have also an impact because of this difference of the transformer ratio on the noise figure. That's why we do not expect this. But we see in the calculation that the transformer ratio does not have an impact.
Okay, thank you, Hugo. Very high-level question. If you had the chance to go back in your PhD thesis, or I'd say to see the next stage of this work, what you would do first to, let's say, to improve the performance of what is coming out from the design you implemented?
Now, for the design we implement, we can work maybe on the mixing parts, because we use first a real conventional mixing. So they have some techniques using even IQ mixing, which allow some reduction of the noise, or even more advanced mixing using multi-phased with duty cycle which are not at 50%. So we can use this N-pace or other mixing techniques to improve the mixing part of the mixer. Otherwise, for the LNA part, we also can try to use some other techniques. Still using this noise cancelling approach, I think it's a good solution to achieve PVT robustness and wideband and low noise performances, but maybe using different complementary approach or cross-coupled approach.
Okay, thank you, Hugo. So I'm satisfied with your questions. Obviously, the discussion must stop, and otherwise could go ahead forever. So thank you very much.
Sure.
Thank you very much. I would pass the word to the President.
Thanks a lot for your question.
Grazie mille, Domenico. We will ask now Professor Bourdel from Grenoble INP to discuss with you.
Okay, thank you, Mr. President. Okay, I would like first to thank a colleague from IMS to invited me in order to review this very interesting work. It's always a pleasure to read works dealing with millimeter waves of RF design, and it's always a pleasure to come in Bordeaux, even by video conference. So first, I would like to congratulate Hugo. I think it's a huge work. I think he did many things, and with a very, I would like to say, with the intention to be very clear with the analytical studies, and it's very, for me, it's very interesting to read such kind of works because all the choices are well, I would say, described and justified. Also, I would like to make some comments regarding the manuscript. The manuscript is quite well written. It's clear. All the schemes are clear, and it's very, how to say, I like to read, and I take very good time reading this manuscript. So for that, and also for this presentation, which is also, I would like to say, in the same wood of the manuscript, also your presentation is quite clear. So thank you, Hugo, for this work and for this good achievement. So I would like also to maybe a last comment. I'm also quite happy because I feel that in your slides you take some you change some few things, and I guess it comes maybe from the recommendation or the remarks that are in the report. So also it's something very good, since you read this report and you modify a little bit a few things. So this is also a good point. Concerning the questions, okay, maybe my first question is related to this the choice of noise cancelling architecture. I saw that you put a specific slide on that, and I think it's something good. And of course, in your manuscript, I believe that the choice was already done in your mind or in the mind of your supervisors. I don't know, and to the end, of course, you finally you change your mind, especially concerning if we focus on the active mixer, and concerning the active down converter. To the end, when you make the comparison to the state of the art, you mentioned the fact that it's quite difficult in CMOS to achieve the performances with active down converter. And your conclusion, if I read your conclusion or your feeling, is that it comes from the fact you are using CMOS, and you do not, I would say, consider the fact that it could be also this issue or this lack of performances could also come from the choice of the architecture. And I would like to have your feeling about that. Are you still convinced that it's not possible to fulfill the requirements with CMOS, or if you change the architecture or consider something else, because you have good reference in your table, the 46 reference is not so bad, and maybe in your system could have good performances. So I would like to have your feeling here concerning this choice of the architecture for active design, active mixer in CMOS.
Thanks for your question. So I feel that we have two questions. First, on the noise cancelling approach, why do we select these topologies? In fact, when we study the literature and the state of the art of wideband receiver, we see that noise cancelling approach is one of the major trends to achieve wideband receiver. And we expect that thanks to this wideband behavior, we can achieve more robustness to PVT variation, which is quite critical for our application, and especially in CMOS technologies. Then why we select this active down converter? Usually, the first radar product was built in BiCMOS technologies. In BiCMOS technologies, we do not have this issue of flicker noise, and the studies shown that we have the best trade-off with this active down converter and active mixer. That's previous work I've been done in my internships. We compare LNA and passive mixer in BiCMOS and active mixer, and we see that active mixer is a good solution because we have this high gain and high linearity at the same time with good or moderate noise figure, at least noise figure which completely fulfill the specification of the car manufacturer. That's why we consider first, coming from this background of BiCMOS designer, that we may have a look on active down converter. And we see that for RF CMOS with more noise, especially flicker noise, that we are not completely fulfilling the application. But we see, for instance, here, if we consider only the interesting performances that we can achieve I would say, moderate noise figure due to this limitation of both active mixer, which not have a very low power noise figure intrinsically, and the CMOS technology, which are not as good as we have before in BiCMOS technologies. So I think these two elements lead to do not consider active down converter for the following step of this thesis. But you're right, it depends of the technologies which we select, especially for CMOS, between CMOS and BiCMOS, and also from the architecture. Maybe some other architecture using IQ mixer will allow a better noise figure, but it requires also, if we use IQ mixer, to have advanced generation for the phases with IQ splitter, which is not easy to implement, especially regarding the PVT variation.
Yeah, but when you several times you said that one requirement, in fact, in the choice, or something that guide you in the choice, is the fact that you need a wideband system. But do you think that with a narrowband, I don't know if it's very narrowband in millimeter wave, but with I would say a topology with a resonance matching, you would not cover, or you would not be sufficiently wide in order to cover your application? Because here I have some doubt, because the last solution you proposed use a transformer. I don't know what is specifically the wideband of the transformer, but you are in the same way of designing, since you are using resonance system that will finally achieve something like narrowband. So, is the choice of a wideband topology is mandatory for your application?
Well, the idea of wideband topology is not to work specially for wideband down converter. It's not the wideband characteristic which is the more important for us, but more the robustness to PVT variation. We expect that using both wideband behavior and specific architecture, such as current mode down conversion, we can be more robust to PVT variation, especially regarding gain and input matching. For the other point, we not use, even if we use an inductor or transformer, an inductive element or a transformer, we are not really resonance, we don't have really resonant matching, because here, for instance, the GM core input matching is defined by the transconductance of each transistor. So we have the GM part, the reactive part is set by this transconductance. Then we have parasitics, but as the impedance is low, these parasitics can have an impact, but not a major impact. And we used this transformer. We use this transformer to both cancel the parasitics, of course, we need it, but also to have this transformation of the real part of the impedance at the input. That's why, even if you're right, we are not completely using a non-resonant approach, I would say, because we have inductive elements. We are not neither on a fully resonant approach, because we do not have a resonance between a big capacitor, for example, a gate source capacitor, and our inductor. That's why we are more in millimeter wave, we say, in the middle between these two techniques. But the wideband techniques, we use it more for the robustness to PVT variation. And we see, for instance, here, depending on the load, of course, but we can achieve very good robustness to PVT variation for the LNA, for instance here. So we have here good robustness from the frequency at the maximal gain, or the frequency at the optimal matching, or the frequency at the optimal input compression point. Or even if we have a look more on the current mode passive down converter, we see that we have also a good robustness to PVT variation. This is linked because we used topologies with low RF impedance nodes, and because we have wideband behavior thanks to this noise cancelling approach based on non-resonant topologies.
Okay, good point. Okay, another question concerning the imbalance. When you design your first active down converter, okay, you are using topology which is unbalanced, and you need to play with the GM of the common source and the common gate in order to compensate for the imbalance. And to the end, no common mode in measurements. So in fact, it seems that you succeed to deal with this issue. And when you go on the next design concerning your LNA, then in fact it is the reason for which you stop using this approach. So that is to say that in the mixer you were able to manage with this imbalance, and not in the LNA. Could you why in fact? Can you explain?
Yes, you're right. It's a very good question. And it's linked to, first, if we have looked more on the noise cancelling mixer, we see here, maybe in 2 seconds, yes, we see here that we have this noise cancelling mixer. At B and C node, we have low impedance node, because first, we cancel the parasitics capacitance at B and C node by the noise reduction technique, the flicker noise reduction technique with these 2 inductors. And then we see at B node the input impedance of the switch quad, so LO plus and LO minus. This native mixer, this input impedance of the switching quad is quite low. So we have a low input impedance. So we have less impact of parasitics, especially capacitance parasitics, on this into current, the RF current, and we are more robust to PVT variation because the parasitic capacitance we may have do not change or do not impact this input impedance, and then the signal, the transmission of the signal. Now, if we have looked more on the LNA, in this LNA, we try to have a high conversion gain. We see in measurements, if I go to the next slide, that we have 15 dB of conversion gain, which is very high for one-stage LNA. So we have here a resonant approach at the output. We have a resonance between the 2 inductors, common gate and common source 1, with the parasitics to achieve a high conversion gain and having a high impedance at B and C node. Because of this high input impedance, we have limited RF bandwidth, because here the mismatch between the frequency, the inductor and the parasitics are narrow bound. So we have a huge impact of the PVT variation. So here, when we do the balance operation, we see an impact of these parasitics, this narrow band operation due to a resonant matching leads to an important variation on the imbalance in phase or in gain. That's why with the LNA approach, which wants to have a high conversion gain, it's difficult to have balance operation using this asymmetrical topology, because it's difficult to compensate for each PVT condition and each frequency the imbalance between the 2 paths, common gate and common source 1. That's why I think this we have this issue for the LNA, but not necessarily for the mixer, active mixer.
Okay, thank you. Okay, I will. I think you have some very good answers to my question. So I will finish here. Thanks again for this this presentation and for all this work. And it was a great pleasure for me to read your manuscript and to attend to this defense. And Mr. President, you have the floor.
Thank you very much, Professor Bourdel. We will go now with your colleague in NXP who follow your work more precisely. So we can begin by Mr. Christophe Landès.
Yes, sure. Thank you, Mr. President. Can you hear me?
Yes, yes, perfect.
Yeah. So, dear Hugo, thank you first of all for all your presentation and all the work you have done. I have to say I'm impressed by the quantity and the quality of the work you have delivered along this almost 3 years and a half now. I will make a few comments and I will also raise a couple of questions to conclude my feedback. Regarding your presentation and your manuscript that I read carefully, there are, for me, not a surprise. They are, in terms of quality, they are completely in line with all the exchange we have had along the course of your thesis in those almost 4 years. The manuscript is very clear, well organized, easy to read. What I have appreciated several points. First of all, the way how you bring the context of your work is very well described. This shows to me that you really understand the radar system constraints that define your circuit performance. In your case, it was about the receiver, the noise figure, the linearity. But also later on, you show that you also master the radar budge link by doing some calculation for sizing your complete receiver chain. I've seen that you pay an attention in having a systematic analytic approach through a small signal model calculation for all the topology that you consider. And for me, this is a sign of the extreme rigorous approach that you have constantly demonstrated. Of course, as an engineer coming from the industry, I really appreciate that you also systematically assess the robustness of all your topology by running worst-case simulation, assessing robustness against the supply voltage and the temperature variation, because this is where the designer in the industry spend most of their time, and it's very important upfront in the frame of this PhD to consider those constraints. But for sure, for me, the most important part of your work is the innovative part, and this complementary capacitor cross-coupled topology. This C4 LNA is really promising. So personally, I'm looking forward the confirmation of the simulation result by the real silicon measurement, because of course, for me, silicon is a real proof of the concept. And by the way, speaking about the expected performance of the complete chain, I've seen that the noise figure of the combination of the C4 LNA plus the passive mixer, with the one which is current driven, the noise figure simulation is still showing a quite large variation over PVT, plus 3.5 dB minus 2. I would like you to give me more insight. What are the root cause and what could be done to limit those variation?
Sure. So first root cause would be on the noise figure of the first stage, so the LNA stage. I will show you maybe the noise figure of the LNA stage first, which is here. So we see here that we have an impact, maybe in few seconds. Yes, here. We have a huge impact of the process and the temperature on the noise figure, especially at out, obviously, here. So how we can improve the noise figure of the C4 LNA? First, we can using isolated bulk for the source of the transistor. We can see here maybe. Sorry. Here, the bulk of this transistor are biased in the P or N bulk, linked to VDD or VSS. And in fact, here we have IC ground, but in the real circuit which is implemented, we have a current control because it allows a current control of the whole circuit. And if we can link the bulk of this transistor to the source using deep and well to have an isolated load or SOI technologies, we can achieve at least 0.5 to 1 dB less noise figure, at least in typical. In typical, we have around 4 dB of noise figure, and we can achieve 3.5 dB of noise figure, which is quite low in millimeter wave. And it also have an impact in for the noise at here at OT. Then we can also have work on the passive mixer using maybe different design techniques to improve the noise rejection, but not the noise, to not increase the noise of the mixer and have a less impact of the noise of the mixer on the overall noise figure. Because you're right, we see a huge important impact, I would say, of the noise figure of the temperature and the process on the overall noise figure. So I see two axes of improvement. First, on the C4NA, maybe using as a deep and well or isolated bulk, and maybe more design technique on the passive mixer to achieve lower noise figure.
Okay, thank you, Hugo. I will mention also later on the continuation of this thesis. Maybe this is an axis for that could be that could be pursued. I would like to step back a little bit about your experience, because this thesis was done in the frame of the so-called contract CIFRE, which merge industrial and academic. And I would like to get your reflection on how this context was bringing to your work.
I think it's a very good solution to make a PhD, because we have both advantages of working on an industrial context. We have a product, we have top-level specification, we have impact of the condition of behavior of this product in a car on our specification. That's the first part. We also have the condition of PVT, which are not always considered for the academical product. And we see that it's very important and which impact a lot our performances and our choice of design of topologies. Also, we have, thanks to our industrial part of this thesis, access to resources, especially for layout, for a lot of engineering knowledge, which allow to have these good performances and at the beginning a good matching between our simulation of our measurements. For the academic part, it's good to have new solution, new idea, new topologies, to have the time also to develop, to try to implement things which can be interesting, but we are not sure. For instance, the active mixer, the flicker noise reduction techniques. So I think it's a good solution to have both academic part and industrial part, and we have a discussion, or not discussion, we have links between these two worlds, allows to have interesting to develop interesting solution and topologies and architecture in PhD work. But it was very positive to have these two elements, industrial and academic one.
Okay, thank you. So for me, your work confirmed that you have acquired all the skill to be or to become an excellent millimeter wave and RF engineer. This is, of course, not a discovery to me or to my colleague Gilles and Xavier, because we made to you an offer many times earlier before you finish your thesis to be sure that you will not fly somewhere else. So I'm really happy to have you amongst the NXP design team. So for me, this is the one of the first very good outcome of this thesis. The other important one is a continuation of the collaboration with the IMS lab, because this thesis was indeed the first one, collaborating with Professor Taris on the radar receiver architecture. There is already one ongoing, more or less, on the continuation with Leo of what we have done. But we want also to accelerate here. We have already signed a collaboration contract, and we plan to start as soon as possible two new theses, basically in the coming weeks or months in Q1. So to conclude my feedback, Hugo, I would like first of all to thank you for all your hard work and your can-do attitude. I will do my best with my colleague to continue to provide with new challenges, because I think you like them. Of course, as many of us here, I regret not to be in the same meeting room and having the pleasure to enjoy later on a lunch together. And of course, I'm missing. I hope that pretty soon we will have the opportunity to celebrate your PhD, and also to enjoy the cookies that you delighted us along your PhD in Toulouse. Thank you, Hugo.
Thanks a lot, Christophe.
Thank you very much, Mr. Hernandez. We can go now with Mr. Urs, if you want to give your comments and questions, feedback, and so on.
Indeed. You can hear me well, right?
Yeah.
Yes.
Okay, excellent. So, dear Hugo, dear Thierry, and dear members of the jury, so first of all, obviously, thank you very much for inviting me today to attend this very interesting PhD defense. Hugo, I started working with you at the time of your master thesis defense. That was back in August 2016. And for me, it's a bit the thing of the end of an era. So really glad to participate to the end of the phase, which I would say successfully completes all your academic education. At the time, it was in Grenoble, at the Grenoble University. It was already on millimeter wave mixer topologies, and you actually mentioned it earlier today during the Q&A. It was on PCMOS, not CMOS. So basically, Grenoble, Toulouse, Bordeaux, and mixer topologies are a good summary of your activity and workplace over the last a couple of years, and I'm glad that you end up and land in Toulouse finally. So we've built with this PhD, it was really the start of building strong relationship with the IMS and Bordeaux University. So when you defended your master thesis in 2016, I discovered that you like to go into detail and that you had an obvious passion for microwave. And over the years, what has really struck me with you, Hugo, is your pedagogy. From time to time, over the last few years, I was asking you sometimes to explain me some complex subject, and you would prepare a 2-3 page summary starting from the problem definition, going through the mathematics, the analytics, the equation, and then explaining the solution and how it would be implemented. So you definitely like to share, you like to explain, you like to teach, and for all of that, you like to understand in depth, and you're ready to start with really going through the deep theory. I think Sylvain Bourdel mentioned it during the questions and comments earlier today. And going through the PhD defense, I would say it's obvious that we could see and read all the amount of theory that you've been going through before. So it was a C2 PhD, and Christophe talked about it as well. The PhD really offers the ability to go and get the best of the two worlds, academic and the industrial.
So, sorry, Xavier, you're quite pulsed now. Not hear well.
You don't hear that well, actually.
Huh? Maybe you may cut off your camera to have better bandwidth for your sound. I think.
I have high bandwidth at home, but I can shut down my camera. Okay.
It looks better now. Maybe. Not at all.
Not sure now.
We don't hear you, Xavier.
You don't hear me? I'm connected with Ethernet wire. I have high bandwidth.
It's better now. It's better now. I think it was your video which had some issue.
Okay. So let me. Yeah. So again, the good thing. I mean, you really made very good use of the fact that it's a Titre PhD and getting the best of the academic world with the rigor of the approach. Requirement to really step back time to time to look through theory, and the automotive industrial world with automotive constraint, ISO constraint, IATF 16949 constraint. So you know what we have in the industrial world is so more focus on the cost of a function, silicon area, which improves ultimately the gross margin, 15 years lifetime, aging effect, industrialization. I think you and I, when we were discussing together, of course, we were really looking at what you're doing with the industrial view. I remember discussing the FMEA, for instance, which is the more typical of the industrial world. And you mentioned in many of the slides, I think slide 9, slide 18, also slide 36, you really insisted on all the PVT. So that's it's pretty clear that you understand the industrial constraint. On slide 33, you mentioned also an attention to the size. So again, understanding that the silicon area is the cost of the
function. Xavier, can you use your wireline, please? Because it's quite difficult to hear you, actually. Can you do that?
I didn't understand what you expect from me.
The wireline.
In the StreamYard, you can have.
It's difficult to hear you.
I am connected with Ethernet.
Okay.
Okay, so I will then just go quickly through my questions. First question, Hugo, I couldn't remember if you were involved a lot into, let's say, layout in 28 versus 40 nanometer. Have you seen many changes or big impact on the layout regarding the performance, or have you not been so much involved into this aspect?
I did not be involved in C40 nanometer layout, but I see a huge impact between our past product in BiCMOS 180 nanometers and the layout in C28. Major impact will be in C28. We cannot. We have to have the more uniform, the more dense circuit with a great uniformity of the circuit, of the transistor gate, of the density, of all the elements. So, and I think it's very, very. We have a huge impact of the layout rules on the layout for C28. That's a very significant impact. We have a lot of rules. So we have, I would say, rules of DRC and AVS, which should be completely fulfilled. But there are also some unknown rules or soft skill rules to have a good matching between simulation and measurements, which are necessary to fulfill. And so we have a huge impact of the layout and huge impact of layout on performances. And also it changed the way we lay out the circuits and the link between the layout and the design, because as we have a huge impact of layout and parasitics, post-layout parasitics on the performances, we have to lay out one block to retune the matching, for instance, to retune our circuits to see if we can compensate the impact of the layout on our circuit and then continue by layouting a flowing block. So it changed a lot the way the layout part and the design part have to talk each other. It's not as a designer, I produce a design, I give it to a layouter, the layouter produce a layout, and then I just do the simulation to ensure that we are in spec. We have more to have this work for each block and see what is the impact of each block on the overall performances. So it's quite different way to lay out it, but I cannot compare to 40 nanometers, but to 180, yes, we can compare that quite different way to work between layouts and design activities.
Okay, merci Hugo. Second question, a bit similar question as Professor Zito earlier, more on the, let's say, what's the most challenging now, and a more general question on the radar. For instance, isn't the let's say third order intermodulation located in the radar bandwidth, or I mean, complex coupling not worse for a radar because of the ghost target than NF degradation? What do you have a sense about that?
Yes, I think the main advantages we can have on receiver is to have to reject or more reject this bumper. So for the two cases you mentioned, first for this bumper reflection with this high compression point, if we can achieve to remove this bumper reflection, we can achieve a better noise figure and gain for the millimeter wave part, achieving a more maximize, I would say, the range of the radar. And the other point will be maybe on this isolation issue, which degrades the noise figure sorry. Here we see the fold mechanism. We see an important degradation of the maximum range. Sorry. Yes, we see on the graph at the top an important degradation due to this lack of isolation. And this isolation is located at the transmitted power, so at the LO frequency. And if we can reject it, rejecting also the bumper, we can achieve higher maximum range without, and we can achieve higher maximum range and having better radar. So I think you're right, it's the main way of improving the receiver, because as we see here with these figures, or even the last one, having a front end, RX front end with a noise figure below 10 dB will not have a huge impact on the performances. Here we gain maybe 20, not 20, but we say 80 meters or a little more for long range scenario. It's not a huge impact. So if we can achieve to remove, to have a filtering of close to the LO frequency, we can achieve both better, easier specification on input compression point for having a lower noise figure, and lower noise figure due to this desensitization.
Okay. So if the sound is not so good, I will stop there. Thank you very much, Hugo. Congratulations. Glad to have you in NXP, obviously. And let's continue building a strong PhD community and relationship with IMS. Thanks.
Thanks a lot, sir.
Thank you very much, Mr. Ours. And then we will go with Mr. Montoriol, Dr. Montoriol.
Yes, good morning. Thank you, Mr. President. You hear me well?
Michel, if you are speaking, we do not hear you.
You hear me?
Okay.
Oh, that's better.
Yeah. Okay, we get you now.
Now, do you hear me now?
Yes, perfectly.
Okay, sorry, it was there was a little delay on the switch. Okay, thank you, Mr. President. Some comments. Okay, I am not going to repeat the comments from Christophe and Xavier. It was a pleasure to work with Hugo during those 3 years, more than 3 years. Yes, of course. Just to repeat maybe a little bit that, yeah, Hugo has shown a very good synthetic approach. He has a very good sense of physical behavior of the circuits, and by being able to make analytical analysis, but also a good synthetic capacity to do synthetic explanation on the circuits. So and also yes, he was well, somebody very with who it is very easy to work and to collaborate. Now, so I have just a few more questions, because some questions I had have already been addressed. But maybe I have a very simple one for to start with. Could you describe a little bit on the maybe on the first circuit that you have done, let's say the noise cancellation mixer? What was the impact of this extraction, parasitic extraction? So if you have, I don't know if you have an example in your slide, but the difference or the impact of this extraction, for example, on the noise cancelling mixer. I remember it was quite surprising.
Yes.
Can you, or just a comment on the fact that, for example, on the noise cancellation phenomenon, what was the impact of the extraction of this C28 circuit?
Yes, in fact, we have a huge impact of the noise cancellation, because at the first time we lay out it as we lay out BiCMOS products. So we do not completely fulfill this real density. So we have a huge impact of not having a uniform layout. So we have to redesign our switches and transistor, because they are not all at the same size. So we have this impact on this uniformity, I would say, for the uniformity rules. We have also a huge impact of the parasitics on the capacitance, especially here it's quite critical. You see at the bottom that we have this series capacitor with this here biasing. So we have some work to achieve to have the less impact of the parasitics here at the input of the gate of the common source, and to have the same small differences in phase and amplitude between the source of the common gate one and the gate of the common source one. So we have huge impact of parasitics here. So we have to design, to tune a little the layout. We have this impact of uniformity. We have also an impact here at the tail of the parasitics, leading to tuning and to change a little and to select how we can implement also this inductive, to have this cancellation and to not add parasitics, to have the good imbalance between the cancellation at each node. So here are the main 3 points. So this one here, which is critical for having a balanced operation. Here at the switch tail, which is critical for the cancellation of the flicker noise, as we discussed before, and the question of uniformity of the layout, which was not completely fulfilled, and we have to redesign some part of this mixer to achieve a good uniformity and to have the best placement floor plan of our transistor in our layout.
Yeah. So okay, and Now, yeah, coming back maybe on the more general discussion, because for this receiver study, obviously we choose to go on C28 nanometer technology. But there are many reasons for that. But if we consider only the mixer design point of view, I would say, do you think that this C28 technology is the best one to make a high performance receiver? Or if we compare, for instance, to the previous BiCMOS technology that we were using?
Obviously, if we compare to BiCMOS technologies for the millimeter wave part of the design, BiCMOS transistor, as we see at the very beginning on the comparison between technologies, the BiCMOS has several advantages. First, they are more robust to temperature, to variation, for instance. They are more robust so they have the best robustness, which leads to maybe less impact on the design, and they have also better RF performances. So obviously designing the millimeter wave part of the circuit, especially at 80 gigahertz, would be easier, I think, with BiCMOS and silicon germanium technologies. But even in deep RF CMOS technologies, if we compare this bulk RF CMOS to maybe FinFET or SOI technologies, we see that we can have an impact of the section of these topologies, of these technologies, on the design. If we compare, for instance, to SOI technologies, we can have first here, if we see at least for my design, the use of the isolated load can impact, as we discussed before, the C4 topologies, but more now if we look more on mixer, BiCMOS technologies are reported to have a lower noise for mixer, especially switch resistance that we see not here, but for current mode, we see the switch resistance have an impact on matching and also on noise performances. And SOI technologies present a very low noise for mixer. So it can be a good solution. It presents also a more wideband behavior, I would say. So it can be also for deep CMOS technology a good solution for products. On the other hand, for instance, FinFET technologies are not reported to have a very high figure of merit for their down converter or transmitter. So for at least the millimeter wave part, maybe it's not the best solution. But as we mentioned at the beginning, now radar products are not the millimeter wave part of the radar product are not the only parameter we have to see, but also the question of cost, question of integration, etc. So yes, BiCMOS technology is the best. Maybe SOI will be the second choice or second preference, but it's not the only. The millimeter wave design is not the only condition that we to select the relevant technologies for products.
Yes, indeed. Okay. Thank you for the answer. Yes, I did ask an overview of all the technology trends we could choose for the future. But that's okay. That's a very good answer. Now, maybe I have. Okay, that's also a comment to say that you have shown or demonstrated an analysis on more than your design, your receiver design, which is of course very good for the future. I have maybe a last question, and because you have mentioned several times that you on the current, well, on the performance of the mixer, especially the LNA plus passive mixer in current mode, in terms of power consumption. What your choice would your choice be different if you don't consider at all the power consumption, assuming that it's not a problem for the receiver? Is there any? Do you see a better solution in terms of performance, noise figure, and intermodulation or linearity? If you relax the power consumption constraint, or if you don't, if you consider it's not a big problem.
I understand your points, Gilles. I think it's a very good question. So if we can consider at least 3 ways to down-convert the signal into have passive mixing. A power-matched approach, which is more traditional in millimeter wave. The voltage or the current mode approach, which will require co-design between mixer and the LNA. We see it maybe in one slide. Yes, here. I think the power-matched approach is very important, at least for transmission, because we want to transmit power, we want to transmit a millimeter wave signal in power at the antenna gain. On the receiver pass, it's less critical because we'll down-convert, and in baseband we'll consider either current or voltage mode. So the thing which is very important is to have the conversion, voltage down-conversion, so the voltage gain, or in the current architecture, the conductance. That's why it's not the question of the voltage or current mode passive mixing is more linked to the RF performances, but the output matched approach will not necessarily lead to better performances. It's more a traditional approach, which is useful to do not have to co-design all of circuits, which improve the way we work, maybe to have more intermediate impedance. But I don't think the impact will be on RF performances, but maybe only on the voltage, the power consumption.
Okay. Yes, okay, thank you. And yes, indeed, you mentioned already the IQ approach, which allows to get some dBs of noise figure improvement. Well, normally 3, but little less in practice. It's also something which allows you to improve performance at the expense of power consumption.
Yes.
And okay, so there is this and the variant that you mentioned already.
Yes, for mixer we can have 4 approach to reduce noise figure and improve noise figure. It's IQ mixing is non-overlapping advanced mixing. So yes, we have these few elements to consider to improve the mixer parts. Yes, but it will lead for higher power consumption. So because we have more complex signal processing at the LO input, in fact, or at the output of the mixer.
Okay. Well, okay. Thank you for this. For your answer, for this explanation. I have no more questions. I think we have already given a lot of comments on your overall work. So I will leave I will stop here.
Thanks a lot, Gilles.
Thank you very much. So just before giving the talk to your advisor, Thierry, Thierry is on mute from 2 hours, so he got a few pages to read. So I just want to take the lead to ask you some questions. First of all, I would want to congratulate you. It's a huge amount of work, not only in terms of quantities, but in terms of qualities also. And your presentation was very clear, and I appreciate it a lot. Just one question. It's a bit related to your previous discussion with Gilles. It's quite clear that the system is quite robust to process and voltage variation, which is not the case from temperature variation. It's not a surprise if you compare with BiCMOS. If you use CMOS, it's less robust. So you did not mention anything about that. So did you have any solution or way to have some of robust topology or robust things to add to the system to deal with the temperature issue?
It's a very good question, which is more linked for our design to the calibration aspect. As I mentioned, I will show you maybe this at the very beginning. As we used active approach with common gate based topologies, for implement those constellation, at the very beginning, we have a common gate approach using the transconductance of the common gate transistor. Maybe if the pointer to be better here. The input impedance and the RF performances are linked to the transconductance of this transistor. So we can use a calibration process in the chain to change and to adjust the transconductance of this transistor to achieve better matching, to achieve lower noise. So to improve gain, noise, or even linearity, if we implement some built-in self-test for noise measurements, which have been already done in radar products, or even linearity measurements, we can adjust this transconductance, achieving better noise performances. In the manuscript presentation, we have an example for the millimeter wave active mixer of this implementation, and we can reduce the noise figure. More linked to, I will show you the slide, maybe here. We see here that noise figure, not this one, here, this one. Noise figure here, for instance, is in a few seconds, is very dependent of the minimal noise figure frequency is very dependent of the technology. As we see here, for the slow technologies, which are with short dashed line. So I will show you here, here, and here. The minimal noise figure is below 80 gigahertz, close to 75 gigahertz. And for the fast process, the minimum noise figure is more at 80 gigahertz. So by adjusting this transconductance, we can change this minimal noise figure frequency and achieve lower noise figure. And for this active mixer, we can achieve, I would say, can save 2 or 3 dB of noise figure, which is significant.
As you play with your GM,
yes,
not only, well, I mean, there's a lot of parameters linked to the GM, you know, the impedances.
In fact, we adjust the impedance and we improve the transmission of the input noise at the output and the input voltage at the output, so we can reduce this optimal matching, in fact.
Yeah, but you need also to adjust the other, because it's also linked to the noise cancellation system, so you need to adjust also the other branch and that's quite not simple.
It's not simple, for sure. It's not simple.
Okay, well, this is just a comment and a question. Thank you again, Hugo. So I will now let the lead to your advisor, so Professor Taris, from Bordeaux IMP.
Thank you very much, Mr. President. And I would like first to thank you for accepting the charge of the president. So thank you very much. Thank you all the people that attend this presentation. Not only the member of jury, I will be back to your contribution after, but all the people online. We have up to 20 person on YouTube, and now a little bit less because it's time for lunch, I guess. I'm going to start with the reviewer, Professor Zito and Professor Bourdel. I would like to thank you very much for your expertise and the big and great job you did in reviewing the report. You put some very good words and very wise comments in the report, and that is very helpful. I like that also people challenge the work, because we go a little bit further, even sometimes really beyond the step we were, with the challenging of people that give another look about the work. So thank you for your contribution and the big work you did for us. Now I'm going to go back to the people from NXP. So let's start with Christophe and Xavier. I get the two of you because something like 5 years ago, I've got this phone call with you, and we had like 2 or 3 phone calls to know each other and set up this PhD. And honestly, I have a very good feeling at the very first call, because we used to talk the same thing. And maybe that was the best way to start a collaboration. So I would like to thank you to contact me and make this happen. Xavier, you are now in another place in Toulouse, but you've been with us for the 2 first years of Hugo, and I would like to thank you for your behavior that can maybe sum up as there is no problem, just solution, and that's true. You always figure it out, and thank you very much for that. Christophe, we keep on working together now, and we try to extend this collaboration beyond the scope of the radar, but also to all the research activity that we can have between the NXP and IMS Lab. As you know, of course, for our lab, it's important to work with a prime company of semiconductor industry. But beyond this point, I really appreciate the people that are behind this collaboration and that make this happen. And honestly, this is very, very nice to work with you. I hope we're going to keep on working in this direction, and then this happens bigger too. Gilles, thank you for your technical support. I remember that the first meeting we had together, when we started to talk about this noise cancelling story, and Xavier was including this one too, we were a little bit surprised because we are very happy about the result, but we still have some guess about the efficiency of the technique, and especially if we move this technique to millimeter wave. And finally, it works. So I'm very happy that we did this story together, and we came up to this result we have together. You're very passionate, and you had to be with us, because sometimes we have good results, sometimes was not good, but at the end, that was a good development we had together. So thank you very much to be passionate all along this technical meeting we had together. I will finish with Hugo, of course. So I will not have any comment about the science, even if I could have a lot still. But a PhD have to finish one day, and the day is today. So let's finish this science investigation today, and let's report this to the next one with Leo and Salim. Hugo, I would like really to thank you for the serious work you did. You really deserve all the good comments that the member of the jury gave it to you, and I joined them for that. I would like also to include that you never neglect any comment. Maybe like I am, you are a little bit scatterbrained, that we forgot some things sometimes. We don't know how, we don't know why, but we forgot the things. And you forgot something in the slides today. but the average value is very high, and I'm very happy that you do this job. I want to also include the fact that you are a creative guy, and that's very important, I think, for NXP. You came up to the C4 LNA by yourself. We talked together. We did not believe in it at the very beginning, but the simulation confirmed that we were right, you were right, and we go on this one. So thank you very much for all this work, and not only the science, because we have a lot of lunch discussion. about everything, and it's always very good to discuss with you. You always welcome here, and you can come back anytime you want. Hugo, you are very welcome. If I can still spend a couple of minutes, we'll give some word in French. Domenico, I give the last part in French for my comment. Voilà, juste pour peut-être les gens qui sont encore en ligne et qui doivent suivre tout ça en anglais, je vais quand même faire un petit commentaire en français, juste sur la partie pour Hugo. En tout cas, voilà, je remercie beaucoup Hugo pour tout son travail, son excellence, son implication. Je crois que tous les membres du jury sont unanimes. Il a vraiment fourni un très gros travail, non seulement en termes de quantité et de qualité. Moi, écoutez, ça a été vraiment un plaisir d'encadrer la thèse. Je garde un très bon souvenir de la partie science, mais aussi de toutes nos petites discussions. Voilà, Hugo, c'est un super gars, et puis j'espère qu'on va continuer à collaborer ensemble pendant un bon moment. En tout cas, merci pour tout, Hugo. Thank you, Mr. President. I give you back the stage now.
Thank you very much, Mr. Taris. So now the jury will meet
Zoom link, yeah.
So we move to
yeah,
Zoom.
for all the members of the jury now, we have to go on the Zoom link for the deliberation.
You have it? Everybody of the jury have
Everybody should have it. Domenico has it because we started together on this one. Par contre,
oui, quitter la salle. Oui, on entend juste que le live s'arrête. Tout le monde.
Ouais, Léo, vous.
Comme ça, on entend tout. Let's check. Tout le monde? Non, pas encore. Christophe, JB, Domenico, Gilles, Xavier. Je crois qu'on a tout le monde. Moi, je vois rien, je vois juste Thierry, Hugo et moi.
Yes.
C'est normal parce que nous, on est inquiétés, on est juste sur le stream. Je remets tout le monde.
Ouais, remettez tout le monde sur le stream. Ok, c'est bon, maintenant. J'ai vu que le remonte.
Ils sont en train de charger.
Okay, so everybody is here. You confirm me that everybody is here. Okay. Okay. So the jury spent some time to discuss and have some comments. So Hugo, I will give you some results of the discussion we had. The jury. So I will try to. If you apologize, Domenico, I will try to do that in French because no, I will not try. I will do that in French because as it is an official way, I will. It's better to do that in French. So please
absolutely,
Domenico.
Absolutely, yes.
I know that you understand French.
I understand a little bit, so that's perfect.
Okay. Hugo, donc le jury a noté et a beaucoup apprécié votre soutenance qui était très claire, très détaillée, et vous avez réussi à garder cette clarté tout en rentrant assez profondément dans la théorie et dans votre travail. Il a également noté les efforts que vous avez faits pour la faire en anglais, avec une très bonne qualité, ce qui n'est pas votre langue natale. Donc, c'est aussi un point très positif. On a apprécié la qualité et la quantité de votre travail. Comme cela a été noté par les membres du jury, c'est un travail collaboratif entre l'industrie et l'université. Donc, avec énormément de contraintes, j'aime pas trop ce mot-là, mais énormément de points liés à l'industrialisation qui n'est pas forcément le cas quand on a des thèses purement académiques, et les résultats que vous avez eus, qui sont à l'état de l'art de ce qui se fait actuellement, prennent en compte ces contraintes-là. Donc, vous avez beaucoup parlé, on en a parlé dans les questions qu'on vous a posées, de la robustesse vis-à-vis du process, de la température, de la tension d'Alim. Donc, ces contraintes vraiment industrielles-là ont été prises en compte dans votre travail. Et donc, le jury a vraiment apprécié ça. Donc, vis-à-vis de tous ces commentaires très positifs, donc le jury a décidé de vous décerner le grade de docteur de l'Université de Bordeaux dans la spécialité électronique. Et je vous adresse toutes mes félicitations.
Merci beaucoup.
Voilà, Hugo, si je vous laisse la parole, si jamais vous voulez remercier le président du jury, par exemple, n'hésitez pas.
Merci beaucoup, M. Begueret. Je veux aussi remercier tous ceux qui ont participé à ces travaux de recherche, donc, que ce soit à IMS, avec Thierry, avec également Magali, Matos qui nous a aidés pour les mesures, avec tous les gens avec qui j'ai pu travailler, ou avec qui on a pu discuter et travailler ensemble ici à IMS, ainsi que tous les gens avec qui j'ai pu travailler et qui m'ont aidé à NXP, donc que ce soit Christophe ou Xavier qui ont été mes managers depuis que je suis arrivé chez NXP, qui nous ont toujours soutenus dans le travail qu'on a fait, mais également Gilles qui nous a beaucoup aidé sur tout l'aspect design millimétrique, dans lequel il a énormément d'expérience. Également Thierry qui a également beaucoup travaillé, donc Thierry Ménard qui a beaucoup travaillé, qui connaît très bien les aspects layout, qui nous a beaucoup aidé pour le layout, ainsi que donc tous les gens en design qui ont toujours fait de très bonnes remarques, des choses très pertinentes, qui ont toujours beaucoup aidé avoir un œil critique et à continuer à travailler sur ces topologies pour chercher à toujours les améliorer, à comprendre à la fois leurs avantages et leurs limites. Et enfin, tous les gens aussi qui ont, dans partie plutôt labo chez nous, laboratoire mesure, qui nous ont aidés à prévoir des mesures pour le premier circuit et bientôt pour le second. Et à effectuer voilà, tout ce travail à la fois de recherche et d'ingénierie, avec des aspects de recherche d'ingénierie. Donc, merci beaucoup à tous et merci également à nos deux rapporteurs. So, thanks Mr. Zito, thanks Mr. Bourdel for your really accurate remark and question on this PhD work and this manuscript and this presentation. Thanks to all the members of the jury. Et merci également à mes parents, à ma famille, compagnons, qui m'ont tous beaucoup aidé, beaucoup soutenu pendant ce travail et pendant la rédaction de ce manuscrit qui a été longue, mais qui est arrivé au bout aujourd'hui. J'en suis très heureux.
Merci Hugo. Many thanks for all the people who have joined the meeting, especially the very North European people. And it was a pleasure to see you far away, but to still see you, Domenico. And hope we will meet together in the future soon.
Thank you, guys. Thank you very much once again, by Terry.
Thank you very much. Thanks a lot.
Okay.
Bye-bye.
We look forward to drink with you all, guys.
Yeah.
Yeah, et j'espère que le repas, enfin, que nous pourrons très bientôt organiser un repas.
Ouais, on vient à Toulouse.
C'est clair.
Et on invitera les Grenoblois.
Avec plaisir.
Thank you, Domenico. Yeah. Thank you, guys.
Bye.
Bye, everyone. Bye.
Bye.
Thank you.
Thank you once again. Souris, Sylvain, souris. Merci, messieurs.